Let's work an example on Newton's second law. So a force of 10 Newton is applied at an angle of 30 degrees to the horizontal, and here is the 30 degrees we have, on a 1.25 kilogram block initially at rest on a frictionless surface, as in the picture. What is the magnitude of the block's acceleration? What is the magnitude of the normal force? As always, we're going to use the strategies that we use to solve a problem. First, we pull out the information that is given to us and identify what it is that we're looking for. So we have an applied force that equals 10 newtons. And we know that the angle it makes is 30 degrees. Right here. And then horizontal on a 1.25 kilogram block. That means the mass of the block is 1.25 kilograms. And it says it is initially at rest. That means the initial velocity equals 0 meters per second. Now we want to find out what is the magnitude of the block's acceleration. So as you can see, I don't put a vector sign because the direction is already given to us. And what is the magnitude of the normal force? So the normal force is a question mark. To solve this, we're going to draw a free body diagram. And remember, our free body diagram is a simple version of our diagram where we model the box or the block as a particle and draw all the forces that are acting on it. So it's very convenient when you do this, put the X and Y coordinate system and put your particle in the at the origin of your coordinate system. Positive X going to the right, positive Y going to the upward. Now let's put all the forces. Now, what are the forces acting? So this object goes downwards. There's an mg, the weight of the object, and there is this normal force from the table upwards, and there is this applied force. So let's put it in our free body diagram. We have a mg downwards. We have the normal force going upwards. And we have the applied force. Remember, we always put the tail of the applied force on the object. It originates from here. Okay. So let's try to really understand where is that 30 degrees. Okay, so if I imitate this situation, the top situation on my free body diagram, this would be my 30 degrees. But the horizontal and the x-axis are parallel to each other. So alternate interior angles are equal. So this is my 30 degrees right here. So it's very important to know. I'm going to put the theta in here. We already have the value for the angle theta. So let me just put the theta in here. And don't forget to label the forces, the vectors. Okay, and it's very important in your free body diagram to draw the acceleration vector somewhere, the direction, because it's very important when you're doing your Newton's second law. Now we apply a Newton's second law to this case where we say sum of the forces equals ma. That translates to into component form of the Newton's second law. That says sum of the forces by x equals max, sum of the forces by y equals may. Okay, So we know that the object is not moving up and down, so there is no acceleration on the y-axis. So AY is, in fact, this guy is 0. So we can say the y components equal to 0. Now, if we expand our equation set, so we need to have x components and the y components. That's why we're going to resolve the applied force into an x component and a y component. So I'm going to do this perpendicular to the x component, x-axis. So this would be my fx going to the right, and perpendicular to the y-axis will give me fy going to the downwards. So once I resolve the f into components, I don't need this anymore. Now I can write my forces on the x-axis. On the x-axis, I have only one force, that is an fx, that equals max, which is the ma that we have. For the y component, we have the normal force mg and fy. The normal force is positive, mg is negative, and fy is negative, equals 0. Now, one more thing, we don't really know what are our fx and fy, but maybe we can do a side work and find it from the components fx. Actually, let me write this down here. Fx is the adjacent side of my angle theta, so that is making f times cosine theta, which if I plug in the numbers, that is a 10.0 newtons times cosine 30 degrees. And then when we plug this into our calculator, we get 8.66 newtons. We do the same thing for the y component. Fy equals f sine theta, that equals 10.0 newtons times sine 30. Plug it into your calculator and that will give you 5.00 newton. So we have two values for fx and fy. Now going back and plugging the values into our equations. Remember, first we want to find the acceleration. So using the first equation here, I can say fx equals ma, a equals fx over m, and fx was 8.66 newtons. Plug in the numbers. Newtons divided by 1.25 kilograms. Plug it into our calculator. That gives us 6.93 meters per second squared. That's our first answer. And then for the second part of the problem, we're going to use the second equation where the n is involved because we're looking for n. So from that equation follows that n equals fy plus mg. And let's plug it in the numbers. So I have a 5.00 newtons for fy plus mg is a 1.25 kilograms times 9.8 meters per second squared, and that equals 17.3 newtons. Well, then the surface exerts a force of 17.3 Newton upward on the block, which balances the sum of the downward force acting on it. That's why the block is not going up and down. Thanks for watching. Stay tuned for more to come.